Hi, my name is John McMaster, joining us here in my Silicon Valley garage.
Hi, I'm Jen Castillo, and I'm not in his garage, and I'll be a voice over everything he does.
So, do you know what this is, Jen?
Hi, I'm Jen Castillo, and I'm not in his garage, and I'll be. That's going to be annoying.
Yeah, I think I turned it off. So, do you want to give a little background, what this object is and why I am interested in it?
So, John, it is a new style of electronics that's been put into some sort of consumer throwaway object. And the reason why we're talking today is because you and I have done a couple of these together, namely greeting cards.
Yes, that's right. And I was taking a walk in El Viso the other day, and I saw this balloon by a lake with a lot of salt water and stuff. And lo and behold, it started singing to me as I picked it up in a nice Elmo voice. And so, yeah, I thought this would be a fun follow-up to the greeting card project.
Yeah, sounds good.
All
So,
right.
what did the original look like?
The original, you mean the whole balloon?
Yeah, like
Oh, geez.
was that the base?
Yes, it did. So I have a picture of it in the meetup. Sorry, in the tweet. Maybe I could actually bring up really quickly.
Mhm.
I could show it to you what it looked like in its native environment.
Mhm.
Let me do a screen share if I can. Just a moment, please. So, is that showing to you? Can you see that?
Yeah. Oh
Yeah.
man.
Yeah, so that's what it looked like. And I think I put like an Amazon version or something like that on the actual tweet. But yeah, there it was. And then you see, I just kind of tore it open a bit and I found that guy in there. Yes, so that's how I got it.
Uh-huh.
So I think with that, then let's start the actual teardown, if that sounds good to you.
Sounds awesome.
Okay, so what we've got here is it looks like there's a speaker over here. And then you can see there's like a little yellow wire running, and that goes into a circuit board on this side over here. So I would say the very first thing that would be interesting to do would be to look up these numbers. I don't know if that's something you want to try to figure out.
I will try to do that. Let me take a picture with my phone so I have something to work from.
Sure, sounds good.
Got it?
Yeah.
Got it.
Cool. So with that in mind, I'm just going to open this up. And first thing I notice in here is this is a relatively similar arrangement to the cards we looked at before. You know, there's a couple of batteries here, and then hopefully you can see that little black guy, this little glob top there.
Yep.
So, yeah, can you tell us what's under the glob top, perhaps?
Usually that's just a bare die directly affixed to the board with a couple of bonding wires out to usually anywhere from 6 to 8 pins.
Yes, and what we're going to try to do is we're going to try to take that glob top off and actually get a high resolution picture of whatever's under there. Now, the other thing that I found really interesting on here is hopefully you can see there are two springs on here. Do you see those?
Yeah, just barely. Can you maybe describe what those were doing in the product?
Yeah, so I don't know exactly, but I think one of them here, it looks like there's a spring-loaded contact on the battery for the one in the middle. I suspect that there was some sort of pull string or something like that on the balloon so that the batteries didn't get drained in storage. So yeah, probably when you unwrapped it, it started powering up the balloon. Now, this second one here is the golden one, which you could hopefully maybe see a little bit at the top. That one I think is motion activated. So I think when you do this, I don't know if you can hear that little ring.
Yeah, that's definitely your cheap accelerometer.
Yes, that is a good description of that. Yeah, so I think this is the trigger on the top and this is the power spring at the bottom. So with that in mind, I think what I'll do is I'll take a quick picture of this and then we'll start actually breaking this down a little bit more.
Sounds good. So if I remember correctly, on another greeting card that we did, we found kind of like a similar, I think what I referred to it in my presentation was a tilt sensor actually. And it's usually just a coil. Is it inside of another canister at all? Or is it just there?
Yeah, there's kind of like a U-strap over it.
Okay. Yeah. So there's basically they're referred to as a really cheap tilt sensor. And all it's doing is that when the spring touches, if there's enough vibration that it forces it to go against the side of the other end to complete the circuit, it basically goes, oh, there must be a tilt. And that usually is what triggers the user interaction.
And stand by just for a moment as I'm going to reposition some things. So this will get a little bit noisy, and I don't know if I should maybe turn off the microphone or exactly what during this. But the next step here is, if you can see this, I think. So I've got a vise here. And typically what I do next is I take something like a Dremel tool. And what I'm going to do is cut this board down so we basically have just that little black area there. And that'll make decapping it a lot easier and quicker. Got that?
Yeah. I don't know what kind of chat access that I have, but I copied the number, the serial number that you were showing that I took a picture of.
Okay.
I'm gonna look up. Upon first glance, it looks like the very bottom says 2019-04-26, which I'm guessing is probably a manufacturing date offhand.
It's worth mentioning the PCB also has 2019-03-15.
Mm-hmm.
And it says ESYS on it.
Spell that again. ESYS.
Yeah, ESYS dash BI. Gosh, maybe BIIS017, something like that.
Maybe you should take a picture before you start chomping.
I did take a few pictures. I can try to send you one, maybe.
Yeah.
Give me just a moment.
Mm-hmm.
I will probably.
The audience is riveted by us transferring information back and forth, no doubt.
I am sure. Any questions from the audience so far? I am sending it to you on Twitter since that's what I have most convenient.
That's fine.
Okay.
I don't think it's a secret.
You can post it.
Okay.
All right, so it's going to happen. Can you still hear me?
Mm-hmm.
I'm probably going to mute the microphone because otherwise it's just going to be really loud.
That's fine.
And then I'll finish. But basically what I'm going to do is I'm going to grind the back of this first to expose the back of this die. And then once I'm happy with that, I'm going to cut the die out of the rest of the circuit board.
So maybe you want to explain why you're going through the back as opposed to trying to break through all of the epoxy on top.
Sure. The issue is that these circuit boards have a lot of fiberglass. And ultimately, I want to get rid of both the glob top and the circuit board. And if I get rid of the circuit board first, which is much tougher, it makes dissolving the rest of it, the top, a lot easier.
Okay.
Okay.
Sounds good.
So I'm going to mute my microphone for a bit then, because there's going to be a vacuum cleaner and a grinder, and it's all going to be very noisy.
Okay. And in the meanwhile, I'll be doing some searches.
Okay. Sounds good. Let me mute.
Somebody suggested that I do some elevator music while he gets set up. So here you go. Na, 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 na. Oh, I hope he doesn't grind off a finger. Na, 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 na. Na, 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 na. I better go do some work. So you see, you got through like the first couple of layers. Give me a thumbs up if you think you're close to the back side of the chip. I guess he can't hear me.
All right, I am back.
Did you win?
I win. I think so. It looks pretty good to me. So this little guy here is now very, very thin, almost to the height of the die. There's like a little itty bitty bit of the circuit board left there, but not a lot.
Okay.
So we are going to go to the next station now. So I'm going to position once again. Give me a minute.
So I'm guessing the next station is the fantastical chemistry area.
Yep.
And we've made it, that last bit of PCB is just gonna come off in a matter of minutes, you think?
Yeah, this whole process, so we're going to do two steps. The first step is there's a little bit of copper left. I don't know how easy it will be to see on that. Yeah, I think you can see that, right? See that shiny?
Yeah. Yeah. Is that the copper?
Yeah, so there's a little bit of copper left. Now I could keep grinding down to get rid of that, but that risks damaging the die. So I leave a little bit on that. And let me just take another photo of this, just in its current state. But the issue is that copper reacts with nitric acid quite strongly. And so if you leave that on there, it can cause a lot of things ranging from the chemicals can get too hot, it can eat up the acid and then mess up the decapping process. So to avoid all of those, I just do a pre-etch step where I just take out as much of the copper as I can. to now, Jen, if you can, also please take a watch on the YouTube, see if there's any questions or anything like that.
I was literally just starting to do that.
Okay. All right, so what I am basically going to do then is I think you can see this here. I don't know if you can actually read this though. So I have 3 bottles here. There is hydrochloric acid, hydrogen peroxide, and water. So what I'm going to do is mix 1 part each of those into kind of a mixed beaker here. And that's going to form a very caustic mixture, which will eat off the metals, but it won't eat off the epoxy. So I'm going to start with some water.
So thus far, we have a couple of comments
Okay.
from Dane, who I think is saying that the ESIS Electronics is in Shenzhen. And is there a way to keep focus on John? We keep seeing, oh, that's because it's me. Sorry, Rusarian.
So maybe what I can do.
Yeah, lock on the Zoom.
Let me see if I can figure out how to do that. I am not technically literate. At least Zoom literate.
You want to pin yourself.
Pin the video. Okay, how about that? So hopefully that will keep the focus then. And as a bonus, I can see what I'm doing a lot better now for you.
Nope, that didn't help.
It did not help. Okay.
Focus on this. I will figure out something.
Okay, well, I did do the pin though, so.
So don't be in speaker view. Be in gallery view. And then
gallery view, okay. So go into gallery view. Does that help?
let me try talking and let's see what happens. And I'll keep watching the screen.
Okay.
Yeah, usually there's about a 5-second delay. I think we're good.
Okay.
Huzzah.
Okay.
Thank you for calling that out.
So what I've done, just to review, so I've added hydrochloric acid and water, and this is not really going to do a lot yet. You can see in there a little bit. But if we add an oxidizer, such as hydrogen peroxide, then this will start to become reactive and start eating the copper. So I'm going to do this. And hopefully, once I add this in over here, if I show you this again in a second, it may be a little bit hard to see on camera. I don't know if you're going to be able to see that. The lighting may not be good enough, but it's starting to bubble. And I'm just going to let this sit for a moment and see if we can at least eat away some of that copper.
So I think they'll be able to see it. And how strong is that acid?
I think the hydrochloric acid is, well, we can take it out here.
A couple moles? What? Or a pH or something?
So it calls it 30%, 32% weight volume, I guess. I don't know how many moles that is, but I think that's fairly strong.
So not exactly something you want to bathe in.
Yeah. It is basically the same stuff, though, you get at the hardware store, so nothing too exotic.
So it looks like perhaps when I was grinding, I didn't quite get all of the epoxy off of the copper. So it definitely dissolved some of it, but not all of it. I think we're just going to call that fine and move on. So what I'm going to do then is I'm just going to start washing the acid off of this to prepare it for acid decapping.
So it's a, yeah, so it sounds like the trade-off that you're making here is like you can cut it really close to get a nice pristine sample, but you might possibly ruin the sample in the same way because the tool that you were using to grind away the PCB wasn't terribly
yeah, and you know,
precise.
I could have really carefully maybe sanded it or something, you know, once we start getting to the end. But yeah, I think for our purposes, it's probably going to be good enough. The worst thing that'll probably happen in this particular case is the nitric acid may get to be a little bit lower concentration, and it might start corroding some of the parts of the chip, but not so much that you wouldn't be able to understand the chip still, so I think that's fine.
So what are you neutralizing the acid with?
I'm actually not neutralizing the acid, I'm just washing it.
Mm-hmm.
So I just washed it 3 times in water, and then I just gave it, I'm going to give it a couple of rinses in acetone just to kind of let it dry off. And then I'm going to put that on just a little like pin wipe or something and let it dry. It doesn't have to be immaculately clean, just enough so there's not a big side effect. So putting this over here. So now we are at the bit where things start to get a little more exciting. So now we're going to start going for some of the stronger chemicals. So I may have to reposition the camera. Think about this. I think that should be a little bit better. Let's see if we can get this to work. So the basic idea of what we are going to do is I'm going to put the chip in this, which is a very chemically resistant high temperature plastic. And the chip will go in here with some nitric acid coming from here. And we're going to heat that and vortex it around just like you saw it doing a second ago. Maybe for about 10 minutes at something around maybe 90 degrees centigrade. And that should very likely fully decap it. So this is where things get a little more exciting. So this is a bottle which contains some nitric acid, a little bit low, not a lot in here. And if you look in here, you can see this discoloration in here, right? You see that?
Yeah. What is that?
So that's nitrogen dioxide, which is built up in this bottle. So when I open this, especially if I blow it, you're just going to see a cloud of red gas coming off of this.
Okay.
And that's part of the reason why I'm wearing a respirator and other safety gear. So when that cloud comes up, it doesn't really affect me in a real serious way. So I've just put the chip in there so you can see it on the little side right there. And now we're going to open this up and add the acid. So you can see hopefully this little, you see a little red cloud coming up there. Maybe if I'm going to peek this, see that?
Yes, I'm going to assume you don't have really good special effects.
No, unfortunately. So here we got the good stuff right here. So I'm going to transfer that into there. Now it's also worth mentioning I'm using a little bit more acid than I typically would. And that's to accelerate this a little bit for a demo, as well as to compensate a little bit for the copper being in there. So I'm just going to close this up first as a kind of a good safety measure. Now, the other thing I do too is even though we've closed this bottle, there's like a little bit of residue acid in this pipette. So what I do is I put a little bit of acetone in here and squirt it up a little bit into the pipette. And nitric acid reacts relatively readily with acetone. And this makes it so that during storage, I don't get any vapors kind of corroding my lab equipment. Okay, so that's been basically neutralized. So now what I'm going to do is I'm going to turn this on. And I'm going to go around and turn on this heat gun.
Okay, so effectively we're agitating, so we're adding motion agitation and then also heat.
Yes.
So O2 to that. I don't know. I don't know if we have any chemists or people in AP Chem who are eager to like write out those equations for us.
Yeah, the reaction is a bit complicated because we're attacking a lot of organics, but if someone wants to go a little bit crazy and write this up, I will welcome it. So I think this is a good point to just bring up a random topic now, if there are any questions or anything like that.
Well, let's see. First of all, it looks like we have Dane, K. Murray, Usarian, who are currently on the chat.
Okay.
Oh, question from Dane. What setting is the Harbor Freight heat gun set at?
So I have to disappoint Dane. That is not a hazard fraught tool heat gun, but rather a German Steno heat gun. Let me,
You mean it doesn't cost $2 and will eventually break?
yeah,
Can't hear you right now.
okay. So I have another one right here.
Oh, okay.
So you can see it right there.
Mm-hmm.
This particular heat gun I like for several reasons. One of them is a better light here because it has a temperature readout on the side as opposed to the back, which most of them have. And that allows me to see the readings a little bit easier. As far as the exact setting that it is on, I believe it is set to something like maybe 200 to 20 Fahrenheit, something like that. And the reason for that is you get a little bit of a temperature drop as it transfers to the vial, but the idea is to heat it up to something in the 90 centigrade range. Please excuse the mix. But mostly that's through experimentation and just finding what works. The main idea is that as you approach boiling point of the acid, it starts to degrade it a lot quicker. So you want to kind of stay away from that and not quite reach that area.
So one thing that I had a question about, like, who's the maker of the card? Because as I'm looking up information, I got to narrow it down. So do you have like, is it American Greetings or who is the maker of the product?
Let's see. Is there a comment from the Discord about a broken link?
I didn't catch that.
Mostly it's Eric. I think it's Eric complaining I'm wearing a mask.
Yeah, yes, I just saw that too. I was like, I think Eric's complaining about how he can't hear you clearly. I guess he just wants you to have acid all up in your face.
Yeah. Although to be fair, I can move away from this if we want no muffle for a minute.
Yeah, I know it smells pretty heavy over there. The closer you are to the acid. I feel like you're dressing up to go outside in Corona weather.
Let's see if I can get these lights out of the background, maybe. Yeah. It's a little bit better. Whew, a little hot in there.
Yeah. Okay. So outside of making Eric happy, let's see. Who was the maker of that? Who's the maker of that card again?
So let me bring up my phone. So it looks like the actual circuit board says ESYS, ESYS. I think that is the best lead that we have so far.
Right. So Dane was kind enough to like point out that that's probably from the Shenzhen, a Shenzhen company.
Okay.
Trying to remember what happened last time I went down this road because like you said, it's remarkably similar to what we had. The biggest difference that I see on this particular PCB is it's round. And all the other ones were definitely not round. And definitely all the card ones in general that I've seen on Alibaba Express have been definitely square.
Yes, and it's also worth mentioning there's one of two vendors that I think I'm expecting once we get the die out. The first would be Sonics, I think is the vendor we've been seeing so far, right?
Yep.
And then I feel the other vendor that might compete in this area would be General Plus or Sun Plus.
What's that company?
Oh, you see them in a lot of like Tamagotchis and other sort of toys like that.
Okay.
Generally high volume, you know, microcontrollers. General Plus, we've seen mostly in like LCD toys or something like that. But I think I've heard that there's also a few of them used in products like this. So I'm going to go check on the stew.
You go check on it. So thus far, what I've picked up from the Shenzhen ESIS lead is when you go to their website, it looks like there's a lot of sleep machines from this company, but I haven't seen anything balloony.
I guess if we also have a moment, I can show a few other things over here.
Okay.
So I don't think that we will need this, but maybe I could show this just for completeness. If I don't know if this is the best view. Let me see if I can. Maybe, I don't know. So the basic idea is, so this little machine right here with the other heat gun is what I use to remove bond wires in most situations. And the reason why I say we probably won't need this is generally high volume chips like this use aluminum bond wires. And this machine is designed to dissolve gold bond wires by using hot solder, which you're seeing right here. And basically I just dip the chip into hot solder here, and that dissolves the gold by dipping it in here. If this chip is aluminum bond wires, instead of that, we're actually gonna have to pluck them off using a microscope or something like that.
So if you have to do that, how steady a hand do you need to make that happen?
Well, depends what you want to do. So usually what happens is there are large stringers coming off. You know, the bond, there's like the chip here and then a big old wire coming off, right? So as long as there's a big wire coming off like that, usually you can just grab that and it just kind of works out. It's not too bad. If sometimes though they'll fold down onto the chip, you have to be a little bit more careful, but I use like plastic tweezers basically, which don't scratch the die surface so easily. So even if I have to kind of dig down on the chip surface a bit, typically it won't damage the IC. Going to check one more time.
Yeah, go ahead, check. Okay, we got Cole Johnson waving. Let's see, who else? So thus far, okay, looking a little deeper at Alibaba for ESIS, it looks like they have maybe some ODM, recordable sound module for a plush toy with a button right on top. It is in a round format. Now, whether that's, yeah, that looks like that is from the same vendor. I'll pop that into the room.
So what I'm going to do is possibly because the copper in there, I think it's not quite dissolving as much as I would hope. So I'm going to change the acid and let it run a little bit longer.
Okay. Should I make some elevator music for you while you do that?
Well, I think I'll probably still broadcast that. There'll be like horrible fume clouds and stuff, so you know, I should let you guys come along for the ride.
Well, if you die, we do want to know what happened.
Yeah, you know, if you were able to control the stream, you could cut it. But if I die, oops.
Well, I did find something to get people for Christmas, a plastic beer opener that also does music or sound anyway.
Yeah. Can you see that cloud in there?
One more time, show it to us. Just a little bit more, as much. Oh yeah, there's a cloud. That was definitely the money shot.
So you probably couldn't see this, but I can see the acid is very visibly discolored. And it's kind of a green color from getting copper dissolved. So this is kind of what our chip looks like now. Not that different looking. And it should have dissolved a lot more than that. So I'm going to wash it and take a quick look at it. Now, I don't know if you're going to be able to see or not. Let me see if I can figure out better lighting here. There you go. That's a little better. Do you see that little shiny bit at the bottom?
Yeah, looks like you're making headway.
Yeah, so we're making headway. So what I'm also going to do is I'm going to try to very gently see if I can break apart that larger black area and see if we can speed this up a bit.
I don't know, man. I know my impatience usually gets me all broken silicon. Be careful.
That is very much a possibility here. But, you know, YOLO, Jen.
Yes, YOLO indeed. Speaking of YOLO, I've been watching this new animated TV series called YOLO Crystal Castle. It's absolutely insane, and I absolutely adore it.
Is that like a Japanese game show?
No, it's an Australian animation for 20 somethings, I guess. Okay, how's that look? Oh, it looks lovely.
Get this so that it's spilling.
Go up a little bit. Okay, I see. Yeah, definitely see the dye.
So it's very spongy,
Mm-hmm.
and it breaks apart very easily. So I'm using is this plastic, which is pretty soft, and I am in fact able to break it apart pretty easily. So
Wow.
what I think I'm going to do then is I'm going to try to manually break it apart very gently, and then we might just wash it after that, and it's probably going to be good enough, or maybe a slight bit of time required in the acid.
Okay. So that is very different than like our past experiences doing that. So it looks like overall, if you have a strong enough acid matched with some good plastic material, good plastic tools, you could probably get through this pretty quickly. And of course, a Dremel to get it kickstarted.
Yeah, and a clarification. So the big difference also from last time as well
was we were also trying to get it to work. So that is, it would still work on the circuit board. And because of that, I was also trying to be a lot more careful and couldn't be as aggressive with the etch cycle.
Good to know.
So I'm going to see if I can set this up, maybe, so you can see as I work under a microscope a bit. Okay, and I'll be back.
Okay, going over to the chat, seeing if there's any other questions that you guys have. I think probably the one question that you usually get, John, if you're willing
Yes.
to entertain, is where can one obtain these harsh chemicals readily?
Obtain. Well, it depends what you're looking for. I would say the easiest for getting into decapping is to use sulfuric acid. Some hardware stores will sell drain cleaners that can be used for this purpose. Other than that, if you go to biodiesel suppliers such as Duda Diesel, those also will sell you those sort of chemicals pretty readily. Now, I happen to be using nitric acid, which is a little bit harder to get a hold of, at least in the concentrations that I am using. For that, the easiest I would say is you have like a LLC or something to buy it. Aside from that, though, it's relatively easy to distill if you are good with chemistry, and that's where a lot of mine has actually come from, because I didn't want to pay for shipping and all that. A lot of times, I've actually made it myself, and that's basically made from a mixture of sulfuric acid and potassium nitrate. It is a bit of work, though.
And the danger level of mass producing that is
Um,
how high?
let's just say that I have some personal evidence to suggest you should be a bit adventuresome to do it. The biggest issue is that you have a high temperature mixture of nitric and sulfuric acid, which is quite corrosive to anything organic, including people. So if you have it spill or something like that, it actually is quite dangerous. Aside from that, I would say it's a relatively straightforward process that a lot of people do. It's kind of one of those things where, if you're not very comfortable with safety and chemicals, I wouldn't attempt it. But if you're pretty competent with lab stuff, you might find it pretty routine. I guess is how I would answer it.
It sounds like whatever happens, at the very least, have some sort of like shower or eye wash station readily available, regardless of how you're feeling.
Yes, I would agree with that. And if you do have a big spill, it could be quite dangerous, I'll add.
Okay. So don't do this on your bed.
Don't do this on your bed. That's right. Definitely a well ventilated area.
Yes, because the last time we did this, I was not in your lab and I opened the door to your lab and the smell knocked my face right off.
Yes, and certainly if you were doing the distillation, the smell is going to be way, way worse because the volumes involved are just much, much higher. Okay, so I have good news. So we have the chip basically decapped at this point. And it was probably hard to see, but I also just knocked the bond wires off. So there were aluminum bond wires, and I just very carefully nudged them off. I was hoping that we would be able, there's a camera on this microscope here that I was hoping we were going to be able to feed into here, but unfortunately that's not working right now. So apologies. I'm trying to think.
Nice pictures, no doubt, later on, and you'll put them up on Twitter.
Yeah, so what I was actually thinking, so what are we running for time right now?
It's at 8:45, so we have about 15 more minutes, I think is what we were targeting.
Yeah, I think we have enough time. So I will try to do then. Let's see if we can squeeze in. I'm going to clean this real quick and mount it for microscope imaging. Does that sound good?
Sweet.
Okay. So let me get a little tray. So first thing we want to do is just do a really quick clean on this. And the way that I'm going to do that is I've just taken a little beaker here and we've got some acetone in this right here. I'm going to squirt this in here and just kind of shake it around a bit and then bring it over to an ultrasonic cleaner and just give it a quick blast. In general, I discourage people from ultrasonic cleaners, especially on older chips or ones that may be damaged, as it has a tendency to crack them. But for this one, which is very small, it's a modern chip, I find the chances of that pretty slim.
Now, when that's in there, what is the likelihood of there being a lot of contaminants that may scratch it anyway?
In my experience, generally speaking, the ultrasonic cleaner itself tends not to cause that sort of damage. The larger risk is if there are chunks that are very tightly affixed to the die, so maybe epoxy that hasn't fully dissolved yet, those tend to get ripped off and damage the chip.
Okay.
So at least in my experience, as long as the die itself doesn't have anything rigidly attached, things in the solution tend not to damage it. Does that make sense?
Okay, so basically structural integrity is going to play a far bigger role than anything.
Yes.
Okay.
That has been my experience. And partly also, I think, just because the volume of solution is relatively large, so things tend to spread out a bit.
Looks like Cole has a question, if you have a moment to entertain it.
Sure, yeah. What's up?
What are the additional risks and challenges involved with delayering a chip? Assuming, because we haven't even got to that part yet.
Yeah, and I don't plan on delayering today for several reasons. Oh, geez. Yeah, that's a whole can of worms. I would say that the short version is the traditional way to delayer a chip involves using a chemical called hydrofluoric acid. Now, if you've heard of blogs like Things I Won't Work With, that is the first entry on that blog. It is a toxic chemical that can kill you on skin contact or, cause you lots of issues. So that has its own set of hazards. It's also possible to use alternate techniques, such as a lapping machine, but those have their own issues getting that set up properly. So the short answer is there's no easy way to do it. That said, if you will catch my upcoming hardware I/O talk, I recently built this wonder machine over here, which I'm going to give a talk on. And that actually does an automatic programmed delayering sequence and makes it so I don't have to handle those chemicals. So that's kind of my special sauce answer for that, which I've started using recently. But traditionally, it's been a very laborsome and somewhat involved, risk-wise process. Okay, so I have just washed this down with acetone a bit after doing the ultrasonic. I'm going to transfer it to another carrier. Now, usually for imaging, I will also mount it on wax to allow me to clean it easier. But I think for the purposes of this, we are just going to place it on top and it's going to be a little bit dirty. But for the purposes of this demo, I think that's fine. So with that, I'm going to change my gloves since these are pretty dirty now from chemical work. And I'm going into a different sort of clean area. And also no more lab coat.
Okay, so we're mostly out of the immediate danger zone and we want to avoid cross-contamination.
In fact, I should say that, gloves at this point really isn't necessary. I do it more as a cleanliness thing than anything else. And since this die is already a little bit dirty, I'm not going to care about that as much. Oh, so I'm having trouble with the door here. Hopefully I didn't lock myself in the garage. There we go. Yep.
Thank God he got out. I was going to say, I'm like, do I have to drive over there?
Okay. So that was kind of the wet lab that we were in before. So this is now what I call the dry lab. So this is where microscope imaging takes place. And what I'm going to do is take a little tray like this and see if I have some tweezers here. I may have to go grab some. I don't see some immediate. And then we're going to put the dye on the microscope. So I will be right back.
Okay, who wants to guess what that blinking light is? So Cole, I hope that answered vaguely your question, which ends up being a like John said, a big can of worms.
So what I've done is I've just squirted some IPA, some isopropyl alcohol on the chip. I'm going to drain it off a little bit. And I'm going to try to very carefully just clean the surface without blowing the dye. It looks like I managed not to launch the dye, so that's cool. That would have made a very anticlimactic finish.
All that work? Where'd it go?
That has happened too many times.
It surprises me a little bit that you don't somehow put it on a sticky pad or something like that when that happens.
Well, that's what I was saying. So usually, yeah, maybe I should show this just for completeness. So usually what I do is I wax mount them. So do you see that sheen there?
Yep.
So that's actually what I would typically do, but since that takes a little bit longer, for expediency purposes for this video, I'm not doing that.
Okay. And just so we know, in case we don't get a chance to see your wax methodology again, is that just kind of standard paraffin, or is that?
I use a technical grade wax called Crystal Bond. Okay. I imagine that other waxes would work as well, and I can send details to that if people are curious.
I was just curious if it had like a higher melt point or something like that.
I specifically selected one that has a relatively low melt point. And it also can be removed with acetone, which makes it pretty quick to get off.
Okay. So I can see here that you're starting to hone in on parts of the chip.
That's right. So we actually have a logo here. So we actually have an answer.
Okay. Can you maybe rotate us towards your laptop?
You actually can see it, unfortunately. I just don't know. Let me see if I can actually zoom it in maybe. So it's a little bit clearer. I just took a snapshot. And I think this will help. Okay, so maybe you can see that. I know there's some glare on there.
Yeah, there's some glare.
I can maybe try reducing the glare. Give me a second.
That like, does it say fun line?
I think it says Sunlink.
Oh,
so we have a chip number there. It looks like maybe that is a 65P00 3MX05A Sunlink 2006-02.
Mm-hmm. I'm wondering if it's just an older chip.
Oh, it's definitely an older chip. So for example, you can see the feature size here is quite large. Maybe what I can do is, why don't I, you know what? I think I actually can bring up the camera feed on this laptop. So why don't you give me a moment and see if I can get something up there, okay?
Okay. So just a quick search for Sunlink. You find a lot of solar power stuff.
So I find that interesting. So remember I mentioned there's this company Sun Plus, General Plus. I wonder if there's any chance that, what is it, Sun Plus or General Plus?
Or what the same, like a subsidiary?
Yeah, like Sunlink, maybe there was a merger and that became Sun Plus or something like that. You know, General Plus Sunlink.
Yeah. Is it Sunlink? It's at the top one is a SSP 003MX.
So I'm now swapping the camera on the microscope to something that I think will work easier. And hold on for a moment while I try to switch this over. Okay, so this is good. So I have a video feed up on my laptop. So let me see if I can share screen now. So hopefully you can see the microscope view application now. Is that correct?
Yes, it is very golden.
Yes. So we could run color calibration and stuff like that, but I think for our current purposes, this will have to do. It looks like we also may be flipped.
Yeah.
Maybe I can correct that real quick. Like that. I think that will do.
Yep.
Okay, so let's also maybe get an overview. Let's see if we can go up on this chip a bit. Okay, so it looks like we have one very large area over there, which I'm going to guess is the sound data. Maybe that is either flash or mask ROM or something like that. And then we have the CPU at the bottom there, or special purpose processor, or whatever it is.
ALU or yeah, whatever.
Yeah, so let's see if we can look a little more. If this will refocus. Okay, so this is the main memory area here. Maybe I can do is I'm going to control this using the motors. Maybe a little easier to move it around. There we go. Yeah, that's a little better. Okay, let's see if we could just find some features just to generally comment on. Maybe I could even zoom in a little bit more.
Can you comment briefly on how many pins this particular chip has going out?
Sure. We can take a look at that first.
Yeah, I know it's terribly boring before you dive in on there, but that might give us some more hints.
Sure. So I think most of the pins are on that side, but let me see if I can pan up a bit. Okay.
Yeah, they're all down there.
Yeah, so I don't know if you can see my mouse, unfortunately.
Yes, we can.
Oh, you can. Okay, great. So you see there's 1, 2, 3, 4, 5. Oops, skipping around a bit. Let's try
So
again.
it looks like you have 3 on the one side, 2 on the other side, and then along the bottom you have 7.
1, 2, 3, 4, 5, 6, 7. Yes. And the other thing I will mention too is it doesn't look like all of these were actually bonded. It looks like you see little marks 3, 4, 5, 6, maybe 7 that were actually used, and the others seem reserved for one purpose or another.
Yeah. So the question goes back to you probably have at least one for power and ground. We had 2 sensors on there or just 1 sensor on the original?
Yeah, there was a few GPIO pins. There was only the one though. One was for power, so I don't think that was a GPIO. I think the other was the accelerometer pin, as you called it, which yeah.
And then the other 2 are probably your speaker.
That's right. Yeah, and I'm trying to remember. There were no other semiconductors on the board, right?
No, there absolutely were not.
Okay, so this would. Yeah, this would have to drive it directly then, right?
Yes, absolutely. So if you take one for power and ground, another set for speaker, another 2 for speaker, that leaves you with 3 pins for those 2 sensors. I would imagine that probably takes care of most of it.
Sure. Yeah, we have some pictures of the circuit board, so if we wanted to, we could do a follow-up at some point and go into a little more detail there. Okay. So if that sounds good, then let's take a look at the actual logic briefly. I know that we're about at our time, though, so if you want to cut it off here, though, let me know. Jen, you hear me?
Yeah, I hear you. You're good to go.
Okay. So maybe on the pins, then, let's start with those a bit and just take a look at some of the structures we see here, because I like this here. I think this is a good example. Let me see if I can get a better view on that. maybe too good of a view, but we can start with that. So what we're looking at here, do you know what this is?
I'm going to go with that's the remains of a bonding wire.
It could be. I think it's actually something different though, because if we looked at the other pins for comparison, I think they looked, or maybe there's a bonding wire.
Well, let's at least maybe a
Oh, I'm sorry. I zoomed in on the wrong one. I meant to go onto the one above it.
Oh, okay.
These guys. So you're right. I think you're right. Yes. So that's right into the bond wire. What about the one above it?
Oh, where there's kind of like a little nick.
Yeah.
So I'm guessing that's probably where the flying probe tester on the wafer probably was.
Exactly. Do you want to talk a little bit about that?
Oh, I couldn't even begin.
Well, what at a very high level is going on there?
It probably went through and it's applying some sort of stimulus and checking to see what the output or input is based on that.
Yeah, and the high level idea is it's pretty expensive to package these chips, especially if you're mounting them directly onto the final product. So they need a way to test the chips, whether they're good or not, before putting them on that final board. Yeah, so put some inputs onto those pins, see if it works, and that way the customer is pretty confident they'll have a working chip at the end. And I would say it's a little bit unclear in this particular chip whether those are IOs that the customer just didn't use in the end, or they are just some sort of internal test pins.
Good point. And so that's all happening while it's still in wafer form. Basically, they're going through the entire wafer and picking out which ones are working and which ones aren't before they cut them out.
Exactly, yeah. And do you know what the traditional thing is when the chip doesn't work?
No.
Traditionally, they'll put a little ink dot on the chip, and that's how you know it's a bad die.
Okay.
Yeah.
Good to know.
Now, the other thing to notice too is we have these structures on the side of these pins. Do you know what those are?
No.
So this is probably ESD protection or maybe drivers. I guess we would actually have to look at them a little bit closer to figure out exactly what they were. But based on that, this is connected to this pad over here, and this looks like a power rail over here. I'm guessing this is ESD protection because there's not a lot else that you would do between most pins and the outside power rails, especially since I don't see a lot of control circuitry going there either.
Okay, so so when you say that you believe that's ESD protection, is it basically just serving as like an insulator, like a large cap? I mean, a relatively speaking large cap, or
large diode, I would say.
Okay.
So it's basically forming an avalanche diode, so that if very high voltage or even a reverse voltage goes onto there, like a Schottky diode, I guess maybe, it'll get to a high voltage, the diode will break down, and the electricity will be dissipated into that diode rather than making its way to the rest of the die.
Okay. So it looks like we have a couple more questions if you're willing to entertain them.
Sure.
Immediate. So let's see. Question. Okay, we talked about that. Is that an Arduino control to that server stage that you're using to go across the chip?
Good question. No, it is not. It is actually running some software called Linux CNC or Machine Kit. And I'm actually just redid a lot of that infrastructure. And I may give a talk about it in the future. But the short answer, no. It's called Machine Kit or Linux CNC if you want to look up more details on it.
Okay, great. And then another question came in around what options do you have for kind of lighting and coloring the chip? I mean, I think like when we're looking at this right now, it looks incredibly golden. That may be, I'm suspecting that's from the lighting source that you have, but maybe you can tell us a little bit more.
I would say even more than that is because I haven't calibrated this camera for this chip. And, when I look at it, let's see if I look at it through here, it does roughly look like that. But part of it is I have a halogen lamp here, and that halogen lamp is causing some of those artifacts. So what I'll typically do is I have a raw silicon wafer here, and before imaging, I would typically do a grayscale calibration. In fact, we may be able to do that really quickly. So let's actually give that a quick try, and that may just work. So That's pretty dirty, unfortunately. But let me see if I can. Oof. See if we
But
can.
while you're stumbling through that, I guess the kind of the follow-on question would be, how much is, are the layers and the chemicals and composition of those layers going to influence the color that you're going to see?
Yeah, so I guess the question is related to maybe like thin film interference or something like that.
Yeah, absolutely.
Okay, let's see if that works. So yeah, this chip in particular, I'm not seeing a lot of that sort of interference patterns. I think you may actually be seeing copper or something like that. It's a little hard to say for sure. When I look at other chips which have that, so actually I have one right here which shows that more strongly. So let me see if I actually can put up the GB Boy CPU, which I think I have over here. So give me just a second. So this is the KF2001. And if memory serves correctly, this actually, you could see some pretty strong interference on it. So I don't know if that color correction was great, but is this still correcting? Well, let me try focusing anyway.
I mean, it's the color of pastel unicorns right now, but
yeah, geez. Maybe hit defaults.
I feel like I made a shirt this color yesterday.
I think this camera or something is having a little bit of trouble picking this up right now. Let me see. Maybe if I go over here, it shows a little more strongly. Oh yeah, I think you can see that there. Okay.
Yeah.
Okay, so it's a little bit subtle, but do you see how this area is more green than this area over here?
Oh yeah.
So this, I would call that a manufacturing defect. That sort of color tint difference is unusually high, especially over such a large area like that. It's almost like this was at the edge of a wafer or something like that, and maybe this chip was still good enough to pass. So when I've seen interference, it looks something a little bit closer to that. You still have these mostly metallic looking traces like we have here, versus the other chip. It's possible that some of the coloring we saw was due to those sort of interference color differences. But I think most of the colors we saw in the other chip was actually just the base materials. But yeah, I can't say for certain. I don't know how much more I can add other than probably this example right here.
Okay,
right
so when you talk about interference, are you basically implying that the thickness of that layer is not even across that, and therefore like you basically are getting like different, like it's kind of bending the light such that it's like showing this different color, like it's shifting the frequency as a result of the thickness variation.
Yeah, and I guess I also should have clarified, there was something implicit there, which may not be obvious, is there's silicon dioxide above these metal traces.
Yeah.
And that's an important part of why you would get that interference.
Okay. So yeah, so I was going to ask also at the top where the ROM is, you have to the right kind of like this bubble, like a larger bubble of discoloration.
Oh, yeah.
The oxide you were talking about?
No, that's something, remember I said we did this kind of abbreviated cleaning process. You know, that could be some old wax that was on my tweezers or something of that sort.
Okay.
I don't think that's actually part of the chip. I think that's just because we didn't clean this very well.
Okay.
We could zoom in on that though. You would probably, I think we can see some cool colors there. And if you wanted to go a little psychedelic.
Okay.
Let's see.
And anyone who's still, we have 11 people right now. If anyone has additional questions about this die, we will more than gladly go there and check it out.
Oops. Yeah, so there's you can definitely see some interference there. So there's thin films from whatever that contamination is. And sometimes you will see that in the layers of the chip as well, although I'm not really seeing it on this one so much.
Interesting.
Yeah, so maybe real briefly, I can also comment on some of the logic here. Just I think this may be a good last thing if we're about at the end here. So what you're looking at here are basically some sort of logic cells. And the other interesting that I would mention here is this chip looks like it uses lambda-based design rules. And what that basically means is that there is a very deterministic unit that the chip is based on as they're spacing the metal across the chip. See how it's very blocky looking and the cells are not very rounded? Do you see that?
Yeah.
Yeah. So that's a little bit stronger even than I would say I see on most chips. And these are probably like the plus and minus power rails here. And then the actual transistors are likely in these areas here. And this is metallization connecting a lot of those cells together. You can see a little bit of another layer there, although it's kind of blown out, unfortunately, a little bit.
Is that the green, the kind of the paler green pipes? That's what it looks like to me.
Yeah, I'm trying to see if we could maybe turn down the exposure a little bit. Maybe we could see those a little better.
Yeah, they're coming in.
And then I'm going to try to focus down a bit. There we go. You can see those a little bit better now. Mm-hmm. So this is maybe metal 2 up here, and then this is metal 1 below or something like that. And those are connecting probably to some transistors around here that we can't really see that well.
So I have to ask, do you feel like this is a fairly modern design? This may be manufactured modern more recently, but do you think that this is like a modern design like in the last 10 years? Or do you think it's older?
Well, I mean, I think the chip itself, yeah, was designed recently, but this is ultimately kind of a economy business, you know, where they really are getting, trying to get the lowest price product out there. And I imagine they're buying old fab equipment, you know, as companies like TSMC don't need it anymore.
Yep.
And that's why they're using this kind of older technology on here. And that's why it's so large, because they're using older, less expensive equipment. Does that maybe answer your question?
I think that gets me where I was going, because given how blocky it is, it really does feel like a older modeling parameter technology.
Yes, it's definitely an older technology.
And not terribly refined. So that's why I was wondering, like, because I'm kind of wondering what on the die, it seemed to maybe imply that it was like from 2002, maybe?
Oh, did we see a year on there? I can't remember.
Well, I kind of interpreted it as a year. What we had there for Sunlink, it was like right after the Sunlink. I think it's in 2000.
Bring that up again.
2005 or 2006, something.
Yeah, 2006. Yeah, I guess the design is actually a bit old as well then.
Yeah.
So the next question then, is that old for 2006? Maybe not. Looks like we got a little.
It's kind of like in between, yeah. So is another question came in. Let's see, decap, not delayered. That's true. We have decap, but we have not delayered the chip.
Yep.
The speaker driver should be fairly sizable. Is it identifiable on the chip? Is something that Dane's asking.
So I actually have not seen any large power electronics on this chip. I don't know what to say about that. We could, yeah, there's not a lot. So I don't know if that means that I've heard that on some very low cost products, and I think this would fit into that region. They actually just do a PWM out, and they rely on the speaker itself to filter the output. So I'm wondering if it's just normal GPIOs and they've just tuned it so it works well with the speaker.
I wouldn't be surprised, given snooping on some of these greeting card style things. It definitely looks like a PWM.
Yeah. If we had another one, I mean, you can get one for $10. Someone could put a scope on there if they were really wanted to trace that out.
Another question came up from Cole. Do you know what the CD of M0 is? And I'm not really sure. Oh, critical dimension is the minimum width of a layer.
So we can't really see the bottom layers. And unfortunately, I don't have a good calibration right now for what I don't know what size this image is. I can take a picture of this later though, and we could probably extract some size information if people were really curious about how big this was.
Okay.
Yeah, oh, actually, you know what I can do is the microscope stage though is size calibrated. So I actually could do is we could move a small amount and we probably could back out the sizes based on that. So let's try that as a quick experiment. So this is a little bit iffy, but let's see what we can do. So I'm just going to put my mouse maybe here as a reference or something. And we're going to have to move a little bit, I think, actually first to get the backlash compensated out of the stage.
What's the backlash?
Oh, backlash is kind of like the slop, you know, when you try to get a gear to engage or something like that, you know, there may be a small gap, so it may have to engage for a second. Okay, so that should get the backlash out. So let's put my mouse here now. I'm going to try to do very small movements, and let's see how far it takes to get across that trace. Okay, that was too much. Let's try smaller. So that was a 5 micrometer movement, just for reference.
Wow.
So let's go smaller. So let's try 1.
Mm.
So I would say those traces are about 2 micrometers across.
Mm-hmm.
So hopefully that gives Cole at least a first order approximation for the sizes involved. We can't really see the bottom layer, so it's going to be a little bit hard to see. You can try to repeat that really quickly on here. Yeah, so I would say at least the traces appear to be around 1 micrometer width.
So what vintage would that put it in? Does it still seem like it's like a 2000, mid 2000s or?
Well, how about this? Why don't we maybe look up Intel CPU nanometer versus time? Mm-hmm. And let's see maybe when was 1 micrometer or 1,000 nanometer? When was 1,000 nanometer a thing? I think that would be a good starting point. And it's not to say this chip is 1,000 nanometer, because the actual transistors, may be much smaller than that. But at least as a reference, a 1 micrometer process for Intel was 1984. And I'm not sure what the relationship is between the metal width and the the actual trace width. So a 250 nanometer process, for example, was 1996. And I'd be surprised if it was off by more than a factor of 4, if I had to make a quick guess. So let's say if maybe this is a 250 nanometer process. That would put us in 1996. And what was this, 2006?
Yeah, well, I would say like if that was the kind of like the top of the line for processors back in 96, then it would probably take a few iterations, maybe a decade.
Yeah.
It went downward to like it was cost effective for these applications.
Yeah, so that sounds about right. So I don't know if that's correct. I would value feedback if someone has a better estimate, but yeah, let's say maybe 250 nanometer-ish, which would put it at about a 10-year lag. I think that sounds like a good start at least.
So Cole's positing that it could be from the late 80s, same turn, and I'm quoting him, same time as 1 micrometer process, and it matches my guess from measurements before. So he's guessing a 600 to 1,000 nanometer.
Okay, so he's suspecting that it's less of a ratio than I was thinking. Yes, that would put it even older then.
Well, I mean, for the cost, so like when I'm looking at, let's say, what Sunlink has, and I can't find anything exactly like this, but when I can look at ESYS and look at what they have there, like if you're going to buy in volume, they can get it down to about 30 cents for including the speaker, including the batteries, including, everything you need. I think you just need to provide like the file with whatever, Elmo-y noise you want.
Yes.
And that's 30 cents per unit.
Oh yeah, that's pretty cheap.
That's incredibly cheap compared to some of the other ones I've seen. And I think all ship it in paper. So you can figure out how you're going to wrap it up.
My biggest regret, by the way, for this presentation is I didn't have the Elmo at the beginning.
And I spent like a whole 5 minutes looking up Elmo voiceover, how to do the voice.
Oh, and
No. Trust me. My partner can do a way better Elmo than I can.
well, that may be a good time to wrap things up then, unless we have any other questions.
Now let's check the channel. Yep, it looks like we answered everything.
Well, I guess thank you everyone for listening then, and I guess until next time.
Yeah. Thank you very much, John.
All right. Good night.
Night.